Thus, in this video, we try to roughly understand first and after more rigorously what is a IID sample, what is a sample which has this IID property. All the variables, all the random variables in the sample are independent and identically distributed. Thus, first, let's think about this sample as a representative sample of the population, which represent correctly both the population, such that you have all the categories of the population that are included in the sample and that are included in a way that does not over or underweight some categories. Male, female, social activity, education, different characteristics of people, ethnicity, and so on. We would like to have a sample which represents correctly all the people inside the population, not overweight or underweight the different categories. It's really complicated. Huh? It's really complicated, and the intuitive idea is to say, okay, to get such a sample, we should be able to pick up individual at randomly in the population. We could imagine that the population is a list of individuals, like an Excel list, like a list of individuals, where you take a random generator, a pseudo-random generator, right? In Informatica, you know, in computer science, pseudo-generators do not really exist, but you pick up at random. The idea would be to pick up at random individuals inside a list, such that we do not intentionally over or underweight some category. And we can say mathematically, okay, if we do like this, the more we pick up samples, the more we pick up data, the more we are close to the real population. Thus, in a way, that is a way to construct a representative sample. This is the best way to construct a representative sample when we think about what should be a representative sample. That means a sample that do not intentionally overweight or underweight some categories in the population. If you imagine that like an enormous Excel list where you pick up at randomly people, and also independently, that means that when you pick up one individual, the next individual that you pick up does not depend on the previous individual or any other individual that has been picked up before. Therefore, if you think about that in this way, you can imagine that we can get a sample which is representative of the population, which does not intentionally give more weight to some categories, Thus, in this course, we are going to consider that the population is infinite. If the population is finite, there are other formulas, but there are other formulas that exist for confidence intervals and so on, but roughly, in a lot of situations, we can consider that the population is sufficiently large to consider that it is almost infinite with respect to the size of the sample that we construct. Therefore, to make things sufficiently simple in this course, we will focus on infinite populations. Therefore, we consider that we have an infinite list of individuals, and in this list we pick up at random. We should be able to pick at random individuals. Intuitively, if we pick up individuals at random without any dependency between the individuals, we should be able to intuitively construct something which is representative of the population, which represents the population. meaning that if the sample is larger and larger, we should in that way reach something which correctly approximates, we should get a sample which correctly approximates the population, which is similar, which is more and more similar to the population. That is the intuitive idea, purely intuitive idea, which is behind an IID sample. But what we sample is okay, individuals, but more precisely, what we sample corresponds to values. For example, in the case of the height of the individual, we pick up an individual at random in the population, and what do we do with that? We look at the person, the individual that we picked up, and we measure its height. This is a digit, 1 meter 75 centimeters. That corresponds to a value, and we have a lot of values. In this case, we can consider that height is a continuous random variable, and in this case, we have an infinite number of possible values for the height of an individual. But we could also sample other quantities. We could only see if a person, for example, is a male or a female. We could sample gender. In this case, we have a finite number of possible values for the random variable. This is 0 for male, 1 for female, or the opposite. Therefore, this is a dummy variable. You have 0 or 1 or 0. You have two possible values for your random variable. Even though the population is infinite, you have a random variable which has two values if it's gender. If it's hair color, let's say, hair color, this is brown, blonde, blue, I don't know, brown, blonde, black, I don't know, a color for hair. Here also, most of the time what you have, this is a finite number of possible values for color. You have, let's say, 5, 6, 7 maximum different colors. That corresponds to 7 values, 7 possible values for a random variable. The idea is to say, okay, first, to fully understand what is an IID sample, let's have in mind that what we sample corresponds to values, and there is a possibly limited number of values or a possibly infinite number of values. For an infinite population, you have an infinite possible number of heights, but you have a finite number of possible genders. If you compute the gender, this is always 0 or 1. You only have two values for gender. Why do I talk about that? This is because I want that we understand this idea of same distribution. Imagine, for example, that we want to sample the gender. If we are an infinite population, we have to intuitively understand that if we first draw, we pick up a random variable who is a woman, there is a probability in the population to pick up a woman, a probability in the population to pick up a man, which is 1 minus the probability to pick up a woman. But in an infinite population, if we go to the second row, we should have, intuitively we can understand that we should have the same probability to pick up a woman or to pick up a man. At the third row, whatever we got for the first two rows, we should also have the same probability to pick up a woman, because the population is infinite. That doesn't change anything if in the first two, that doesn't change the probability to pick up a woman in the third row, if for the two first rows you picked up already a woman. If you picked up two men for the two first rows, the probability to pick up a woman at the third row is the same as if you had picked up two women for the two first row. Thus, you picked up two men for the two first row, or you pick up two women for the two first row. That doesn't change, that should not change the probability to pick up a woman at the third row. And that obviously does not change the probability to pick up a man at the third row. Because we have an infinite population. If you pick up a woman, if you remove a woman, that doesn't change the population, it is infinite. This intuitively, this assumption should be understandable in that way. The probability to pick up a woman does not change according to the draw, according to the first, second, third row, nth row. Thus, the probability, in this case, the probability, this is the distribution. In the case of gender, the distribution, therefore you have a probability to have a man and probability to pick up a woman. This is a Bernoulli distribution with a parameter p. This is a discrete distribution, but in general, that means that for a sample, for an ideal sample, for a representative sample, we are going to make this assumption that the distribution of the random variable is the same at each row. Xi, the distribution of Xi, is the same whatever the distribution, whatever I is. At each row, you have the same distribution for the random variable. And the distribution of that, this is the distribution f theta that we presented at the beginning. In a probabilistic world, we study X, which is the height of an individual in the population. Obviously, the distribution of X was f theta. And here, when we pick up Xi in the population, an Xi with that, this is exactly a random variable of the same type as X. X is the height of the individual, but what it is in a probabilistic world, the height of an individual, this is the probability when you pick up an individual that its height is a given value, and you compute the different probabilities for every value of the height. But Xi, it is the same. Xi, this is, you pick up an individual in the population, and this individual, it has a lot of possible values for the height, and it has a distribution. Therefore, Xi, and what we want with this assumption is to say, okay, at each row, the distribution of Xi should have the same distribution. This assumption would not be true if we had a finite population. If we had, for example, in the population 1,000 persons, if you pick up a woman at the first row, you have still 999 persons in your sample for the second row. The probability to pick up a woman is not the same as in the first row, because you remove the women for the first row. Since you picked up a random, since you picked up a woman at the first row, at the second row, in your sample, you have only 999 data instead of 1,000 data, and thus the probability to pick up a woman changes. It doesn't change if you construct a sample in the case of a finite population. It doesn't change if you pick up at random an individual in the population, but with replacement. That means, in this case, if at the first draw you pick up a random variable, it is a woman, okay, you note that in your sample, and after you put the woman back in the population, for you, in this case, you replace, this is with replacement, you replace the woman in the population. In this case, at the second draw, the probability to pick up a woman is the same as the probability to pick up a woman at the first draw. Because in this case, okay, with finite population, you understand that it's immediately more complicated. Huh? If you want to have the same distribution for each draw, the same probability to pick up a woman at each draw, you should sample with replacement. After the first draw, when you have a woman, okay, I have a woman, but I put it back in the population, in my 1,000, in my population of size 1,000, I would say. And thus, draw after draw, in this case, you have the same distribution for each xi. But this is the case of a finite population. We don't have this problem with an infinite population, as we said. Thus, this assumption is really important, this assumption of same distribution that makes that all the xi's have the same distribution as x. X, the characteristic which is studied in probability, the height. This is the quantity x which is studied in a probabilistic world where x is a characteristic for which we want to study the mean. Here we have different xi's which have the same distribution as x, and we want that at each draw we want to have the same distribution for xi. And obviously you can understand that this kind of assumption is really important for calculations. Since our objective was to compute the distribution of xn bar in the previous video, we can easily understand that it's easier to compute the distribution of xn bar if all the xi's inside this sum have the same distribution. The other interesting assumption is to say that all these data should be independent. Imagine that you have to compute the variance of 1 divided by n sum of xi's. If all the xi's are independent, you have the variance of a sum. Variance of a sum, you know that involves covariances. But in this case, if all the xi's are independent, the covariances are 0. Thus, when you compute, if you want to compute the distribution of xn bar, one of the way to compute the distribution of xn bar is, okay, that can be to have an idea of the distribution of xn bar. You can compute the variance of xn bar. If you want to compute the variance of xn bar, you immediately see that it's easier to compute this variance if you have independency between all the xi's. Thus, mathematically, this assumption of independency is also very interesting, but in practice, this is the same idea as representativity in the population. In my list, in my infinite list of individuals, I use the random generator, and the random generator, what does it do? It picks up at random individuals independently of each other. If you picked up an individual with that characteristics at draw I, there is no reason that you pick up at draw I plus 1 an individual with the same characteristic. The characteristic of the individual picked up at draw I has no impact on the characteristic on the individual picked up at draw I plus 1. The characteristic of the individual picked up at draw I, more than that, has no impact on the characteristic of the individual picked up at draw J, for J different from I. This is independence. And with a random generator, you can achieve that. Okay, this is equivalent that amounts to intuitively picked up at random people, okay, without giving more importance to some category in a blind way. That is what is interesting with this independence and independence property. Thus, if we have both together, we have the xi's that are independent and the xi's which all have the same distribution. That means that we have an IID sample, I for independence, ID for identical distribution. That means IID sample. In the case of infinite population, IID samples are also named, and most of the time we name that like this, simple random sample. Simple random sample. This is a way to sample. We say that when we have a simple random sample, okay, we can do statistics, at least basic statistics. We can do inference, we can compute confidence intervals, we can make hypothesis tests that will be seen in another video. But okay, with a simple random sample, this is an IID sample, we can construct statistics. We can make we can construct confidence intervals, to be more precise.